second. I'm leaving. I'm leaving. If you have the exam, I won't take it. Go. I mean, I already told the student. I don't know if somebody else is.
When do you need this?
1 week. I think it's not much. Looks like that many students only done 1 page, so it's not. Okay, we can communicate. One student didn't know the. Now? Okay. I don't know if there are more people, but it's okay. No matter what I say, they don't pay any attention. So one student forgot the ID. He didn't know his ID. Then I take a picture, a photo, I will send to you. Okay. With the name of the student so you can then find it. I don't know if this student is still is. Sorry, today was no problem.
I may have something important tonight, so I may go out halfway.
Okay, that's totally fine.
Thank you.
Okay, hi everyone. So it's already almost the last lecture. So naturally it means that we can do a little bit more advanced topics now, which are not super relevant for the exam, but I think like relevant that you should know them. So one of the topics is like what we discussed today. It's the what is called a fundamental theorem for surfaces. So that's the topic for today. For surfaces. So there are a lot of fundamental theorems. We already have seen the fundamental theorem for curves, which was saying that once you give me the curvature function and a torsion function, I can reconstruct the curve that has that as a curvature and a torsion. So that was for curves. We already saw that. Was that we can reconstruct the curve from the curvature and torsion. So what would be the analog of that for surfaces? What do you think like I need to specify in order to reconstruct the surface? What kind of information do I need to give you that you can say, that's the surface that you were looking at? So does someone has an idea what you need to specify in order to reconstruct the surface? So the analog of the curvature would be the Gauss curvature, right? So the natural guess would be that we can reconstruct the surface from, like first guess would be the Gaussian curvature. So let me make a question mark there because maybe it's not enough or maybe it is. So actually it turns out it's not enough information that you need. So to reconstruct the surface uniquely. Why is that? Does someone know like a counter example where it's not enough information that we need to specify the Gauss curvature? Does someone has an idea? What about you? Okay, that's the second one, okay. So it's first fundamental form. But what about like the Gauss curvature? It's like why is it not enough to specify the Gauss curvature? What? Okay, so if you have like isometric surfaces, then you might be have the same Gauss curvature. That's like a good point. But actually, even if you consider, if you say like let's reconstruct the surface up to isometry. Like, then you still have like the problem that, for example, the plane has the same Gauss curvature as the cylinder, and they are locally at least isomorphic. That's true, but not globally. So that would be, for example, one a problem is like that. For example, the plane and the cylinder. Then have both the Gauss curvature equals to 0. And then what you said, it's like it's also intrinsic information. Intrinsic. So that means that it's not able to detect non-isometric like surfaces, but there are even examples also surfaces with the same Gauss curvature, which are not locally isometric. Which are not isometric. So the Gauss curvature is not even enough information to, let me put the first fundamental form on the next page. So like the Gaussian information, Gaussian curvature would be a natural guess, but it's just like not enough information. It's like you have too many degrees of freedom. It's essentially one function, and we call that with the curvature and the torsion. And actually, there was like the third function, which was saying that it was the constant one function that we always said we have like constant speed or unit speed curves. So even in the case for a curve, I needed to specify three functions. The Gauss curvature is just like one function. So it's like not enough information just to reconstruct the surface. So the next question would be, like, let's give a little bit more information, namely the first fundamental form. But the first fundamental form doesn't tell you anything about like what the normal is doing, right? So you have absolutely no information about what the normal is doing. If you just give the first fundamental form, that's the inner product between the tangent vectors, you have no idea about the normal direction. So someone else has an idea what kind of information we need to specify? So it actually turns out that you need both, the first and the second one. And that will be in some way, like the discussion today is that indeed, once you give the first and the second fundamental form, you can reconstruct the surface. I give like then the concrete statement at the end of the lecture, or no, at the end of the first part of the lecture. But now we would like to discuss a little bit how that may look like, that you can construct this first and the second fundamental form. One problem, however, is like what it actually means to give the first and the second fundamental form, because the first and the second fundamental form are like bilinear forms defined on the tangent space of the surface. So how do you give yourself a first and a second fundamental form without giving the surface first? Like there's no way to say, okay, like what is actually a second fundamental form if you just like don't have a surface, because they are intrinsically defined on the surface. So that's the first problem. Forms on the tangent space of S. So we need to specify to have the surface first in order to specify so that's like a bit like a circular reasoning. If I say like how do you reconstruct the surface from the first and the second fundamental form, but in order for you to give me the first and the second fundamental form, you first have to write down the surface. That's a bit like a illogical question. So the best that you can hope is to actually reconstruct the local parametrization. So not like the surface in itself, but what we can hope is from the local representation of the first and the second fundamental form. Because the local representation of the first and the second fundamental form, they're just like a bunch of matrices, or matrices parameterized by points. So that I can give you prescribe without knowing the surface. And then you say, okay, can I actually reconstruct the local representation? So locally, can I reconstruct the surface? So assume that if S is a parameterized surface, say via a parameterization, which we call psi, and the following. So that's a map from some open subset of R2 into R3, and the image of that is the surface. Then we can pull back the first fundamental form and the second fundamental form. And as you have shown in multiple homeworks by now, you get two matrices, which are called G and L usually. So these are families of symmetric matrices. Parameterized by points. Of the domain that we are looking at. So the question would be now oppositely, if we have given two symmetric matrices parameterized by points, like G and L, can we reconstruct psi and the first fundamental form and the second fundamental form on S, such that if you pull back what we could reconstruct by this psi that we construct, we then get an G and L back. So that's the question that we would like to ask. So given two matrices, G and L, again parameterized by points in D, can we reconstruct a psi, which is a map from D into R3, with the first and second fundamental form on psi of D, which is then the surface, such that if you pull back the first fundamental form, you get G, and if you pull back the second fundamental form, you get L. And the answer will be yes, that's possible under natural conditions on G and L. So let's assume that we start with that G L. We already can assume that they're symmetric, so because otherwise it's not, there's no much sense, because the first and the second fundamental form are symmetric. If you pull back, you still get something symmetric. So we can start with two symmetric matrices. With each entry being smooth functions. On G. And over here, we'll now consider like one example that we will discuss like in parallel. And the example will be, let's assume that G is given a squared plus 1, 0, 0, e squared x squared, and L is given by a over x. And A is just like some number which is fixed for this example, and D in this case is the set of all points x and y in R2, such that x is positive and y is an element of 0 to 2 pi. And the question would be, okay, how do we reconstruct, or is it possible to reconstruct a surface that has G and L as the local parameterization of the first and the second fundamental form? Okay. So how do we do? Like first of all, we have to also assume that G is positive definite, because it needs to be an inner product of tangent vectors. So we also assume that Gi or G is positive definite, which says, for example, you can say that the eigenvalues have to be positive. And you can see that from this expression, that's clearly the case. This is a positive number, and this is also a positive number. So that's already satisfied. And the idea of like reconstructing the surface is that we use again the power of the Frenet. Like for curves, we use the Frenet frame in order to reconstruct the curve. So we first reconstructed the Frenet frame, and then from the frame we reconstructed the curve. And the same kind of approach will be used for the surface. Instead of the frame, we used our local frame, or like the dual frame in terms of the connections forms. So that will be the idea. So what we do is like E1 and E2 be an orthonormal frame of R2 on R2, or on D of R2. And orthonormal means not like with respect to the standard Euclidean product, but with respect to G. So we take like the inner product, or like the matrix we multiply on both sides with respect to G. So the E1 is like easy to write down, and actually you can do that by just. So that would be we can choose maybe as E1. because if you plug in E1 into a G, then you get like 2 times or like the square of G11. So we normalize that. So that one would be easy. E2 is a bit more complicated, and if you think about it, you end up with the following formula, which is not so important, but the point is that that there is a formula that tells you, in terms of G1, how to get a local frame, E1 and E2. And omega 1 and omega 2 will be the dual frame. Theta. So that will be the dual frame. And we can do that for our example over here. In this case, we get E1 being just 1 over the square root of A plus 1. So we take the square root there. And this relatively complicated formula for E2 simplifies in this case that we also just take the square root of this expression here, which leads to this expression here. And then we take the dual basis of that, which you can calculate to be a theta 1 dx of phi 2 being ex dy. So that's the dual frame that we get. So the point is that we have theta 1 and theta 2 in terms of G. So these ones only depend on G. I think the next step you can already guess. Once we have theta 1 and theta 2, we can also get one of the connection forms by the usual equations that we already used in the proof of the Gauss theorem. So omega 1, 2 by the structure equation. So that means we have d of theta 1 equals to omega 1, 2 wedge theta 2 and d theta 2 with a minus sign 1, 2 wedge theta 1. So if you do it here, then you get, like, first of all, d theta 1 is just 0 because it's a constant function. And d theta 2 gives you a times dx wedge dy. And then from that you can conclude that omega 1, 2 is equal to a over square root of a plus 1 dy. Okay, who has an idea what we do next? We haven't used the second fundamental form at all, right? So this one also only depends on G. What do we do with the second fundamental form? Well, like we use the structure equations to define omega 1, 2, so it's also natural to use the structure equations to define omega 2 free and omega 1 free. And the structure equations were given in the terms of the second fundamental form. So we define omega 1 free as the sum over I and j over Li dx I in terms of E1 dx j and similar, omega 2, 3. Also sum over I and j. But here we take dxi e2 dxj. So that's like the formulas, the normal structure equations that you would expect if L would actually be the second fundamental form. But like we called it, like the setup was, we don't have a surface yet. So we pretend that we define this time these functions or like these connection forms. So in our example, what we have here would be omega 1, 3, just 0, because there's a 0 row, and omega 2, 3. If you do, what we have to do is we have to evaluate dy on E2, and that gives you this factor of 1 over x. So if you write it out, what actually, like this 1 over x then cancels this 1 over x, so what you end up with is this form, which is dy over the square root of a squared plus 1. So we have like our connection forms, at least like the local version of that. And once you maybe I will still write it here. So if G and L would be coming from the pullback of the first and second fundamental form, then we would know that these connection forms would satisfy the Gauss-Codazzi equations. So we have these Gauss-Codazzi equations. So these equations would hold, so that's the Gauss-Codazzi. So these would hold if like omega 1, 3 would be the local version of the connections that we had defined in terms of the second fundamental form. Then we proved last time, or one of the last lectures, that these equations hold. But now there is no like a reason why these equations should hold. If I start with some arbitrary G and L, these equations, like if I do the procedure of defining like omega 1, 2 and omega 1, 3 and 2, 3 by these equations, then there's no reason why these three equations should hold. So in this case, they impose some conditions. Conditions on G and L. And actually, you can imagine that already if you start from E2, then omega, like already the omega 2, like the theta 2 is relatively complicated, and then you take d of that. So that gives you already relatively complicated formula for omega 1, 2 in general. And then you have to take omega 1, 2, and you have to take a d of that again, and then require that that's connected to the L. So there's like, if you write these formulas out, they're actually quite complicated. So I would call them ugly. So I will not write these equations down, what it means for G and L to satisfy these equations if you write them out. Like it's, you can see them equations if you want in some books, but yeah, I don't want to write them down. So the point is that not every G and L like arise in that form, but they need to satisfy these equations once you have omega 1, 2 and omega 1, 3 and 2, 3 defined by this procedure. So let's check in our example that these equations are satisfied. So in this case, the Gauss-Codazzi equations would be if you take d of omega 1, 2, that's a constant, so you get 0. And by this equation, it should be omega 1 free with the omega 2 free matched. So omega 1 free is 0. So in that case, this equation holds. And in a similar way, you just verify that actually all of them are 0. This one is clear because omega 1 free is itself, and omega 2 free is also, if you take d, it's just a constant, so you get like 0. So, and then you verify that if you take these wedge products on this side, these wedge products, then you also get 0. So in this case, everything works out really well. And these Gauss-Codazzi equations are satisfied. And then there's a result. That says the following. Assume that these omega ij satisfy the Gauss-Codazzi equations. Then for a given point P0 in R3 and a frame at that point, which we will maybe call F1, F2, F3, orthonormal frame. Or actually, orthonormal basis might be better, so it's a constant orthonormal basis of R3. So just 3 vectors which are orthogonal. That's our input. Then this lemma says that there exists a unique smooth function, which is actually happens to be also injective, but into R3. So it's injective and non-degenerate. And smooth functions E1, E2, and E3 from D into R3, forming an orthonormal basis of R3 for each point that we put in there, such that the following equation holds, namely if you take the tangent map of that map here, of the psi, you get theta 1 at a point x, y, E1 x and y plus phi2 . So that's the, by the way, the equation that you would expect if you just take saying that E1 is the pullback of that these ones are really the pullback of the first fundamental form by this map. And then we have the second equation, which gives the derivatives of the E's. And as you expect, that would be given in the connection forms. So these are the structure equations that you know. But the point is that this time we start from omega ij and theta 1 and theta 2, and then impose these equations and find the psi and the E1, E2, E3 as the solutions to this equation. So that's the important point, is that these are structures equations, but these ones are now, the right-hand side is given, and the way that we derived the structure equation was actually starting from the left side and then said, okay, there should be some coefficients, and we call them omega ij. But now we do it exactly the other way around, where we define psi and E1 by these equations. And the connection with the P and the F is, of course, given by that at 0, you get P0, and I at 0 is given by this F1. And the point is also that they are unique. The idea of the proof is very similar to the idea of the proof for the fundamental, or like the similar statement for curves, which was some kind of ODE proof that like you can have like a solution to an ODE. It's similar in this sense, but it's a bit more complicated. And it's, what you need in this case, it's what is called the Frobenius theorem. But, so the proof is actually quite involved. The important point for us is that there exists a solution, and that solution is unique. So let's do it in our example here. So what we get is that t psi equals to square root of plus 1 dx, and then in E1 direction, and ex dy in E2 direction. So if you plug in a vector here, you have to plug in the slots dx and dy. And similarly, we have t of E1 given as a over e squared plus 1 dy E2 t E2 given by and t3 are given by dy over and then the best way to solve these equations would be just ignore for the moment the first one. So we first solve essentially these equations here, the second part. And then once we have the solution, we can solve the first equation. This one means that if you take the derivative in x direction, you get 0 for E1, but if you take the derivative in y direction, then you get a over square root of a plus 1 in the E2 direction. And yeah, like to make the story short, you just solve these equations, and what you end up with is of cosine a cosine y, a sine y, and 1, e2 you get minus sine y, cosine y, and 0, and e3 is given by 1 over minus cosine y minus sine y and e. So I hope I didn't make any mistakes by calculating, but you essentially, like either you try to solve them like iteratively by giving like differential equations and then solving them, and easier of course is if you have E1 and E3, then you just check that if you take the derivative of that one, for example, in the y direction, you get E2 back and stuff like that. So yeah, so you get E1 and E2 and E3, and then once you have that, you go back to your first equation, which gives you also equation for psi, and then what you end up with is the following. Given as x times a cosine y, a sine y, and 1. So if you take the derivative in x, you get the first vector, which is like E1, so that satisfies the first part. And if you take the y derivative, then yeah, essentially you get E2 again from taking the derivatives. So so that's the way that you get like these psi these important data you get by solving this equation or these equations. Okay, and then the point is now that we once we have the solution to these equations, then we have the following, that we define S to be the image of the solution, is then parametrized my surface with an adapted frame E1, E2, and E3. Strictly speaking, we have to compose them with psi to get really a frame on S, but I think that should be understood. So now we have to show that once you say, like, now we take the first fundamental form of and the second fundamental form, that if you really pull back these data with psi, that you really get like G and L back. So what we still have to do is we have to check that. If you pull back the first fundamental form of that surface, you get G, and if you take the pullback of the second fundamental form, you get the matrix L back. Okay, so let's do that. Namely, let's say we verify it in the 1-1 direction. So we evaluate it as on dx and dx. So the first step is, if I write something like that, the only thing that I can use is that this one is defined as a pullback. There's nothing else that I know about this left-hand side. So I expand what it means to be the pullback, which means that we take evaluate the first fundamental form at that point, and we have to take the derivative of the map in the x direction. Well, so now the problem is that the only thing that I know about the psi is that it's a solution to these equations. I don't know anything else than that. But that's okay. So now we can plug in this first equation that we have for this product, or for these terms there. So what we end up with is that theta 1 x and y, and in the v direction, but v is in this case dx. So here we get dx e1 plus d phi x dy in the x direction, and then e2. And similar expression comes from this part here. Now, the point is that we now know that E1 and E2 are an orthonormal basis. So that's the orthonormal basis. So we know that we can calculate these inner products very nicely. So what we end up with is that we get this one squared x squared. And similarly, we get this term